Complexity is definitely increasing. The behavior of all interesting systems is emergent. It's a function of not just the individual behavior of its little pieces, but the way they collectively interact as a whole.
Any of the components can go wrong, any of the combinations of the components can go wrong, and many of these systems are very timing dependent. Even if they're functionally correct, the combination when you have to do it in a given period of time can get very, very complex.
This problem is actually upon us, and it is going to get worse. It's become always on, always connected.
Everybody wants tomorrow to be better than today.
Now we're looking at 100 gigabit data centers. What follows 100 gig is 400 gig, and what follows that is 1 terabit.
People are packing more chips on board than ever before. We're putting chips into smaller packages than ever before.
You get a lot of interactions. You can define really well the functional behavior of the individual pieces, and you can test them and you can thoroughly vet them out. But when you go to aggregate them together and you sort of hook them all up into something that's big, the way they interact can be really complicated.
And that increase in complexity has created an increase in debug time.
When the designs grow in complexity, the difficulty of design verification grows in complexity.
I've spent a lot of time in labs with logic analyzers connected to systems that I've designed or built or worked on. A lot of times I don't really know what I'm looking for. The system's maybe not behaving the way we think it should. We don't really know why. We don't really know where to look.
Verification is a huge challenge, every bit as large as the design challenge.
If you get quality wrong, you took a year hit in your time to market, and you probably don't get a second chance.
Fewer than 1% of the engineering projects that I'm familiar with have met their verification schedule.
Workarounds are eventually going to not be enough. We've been dumbed down a little bit to accept mediocrity.
The current situation is like a doctor that has no x-ray, right? They can observe what's happening externally, the heart's not beating correctly, but you're not allowed to see the inside.
It's a little black box, and you can't reach inside it.
And you're basically spending a lot of mental energy trying to hypothesize what could be going on that causes the system to behave this way, when many times the answer is just deep inside there somewhere, where some gate, some flip-flop, some signal, some piece of software didn't do what it was supposed to do when it was supposed to do it.
The bigger the system is, the more expensive those experiments are to run. It takes a longer time to set it up. Have I controlled all the other things that might be going on so that I can test my one little hypothesis?
How big of a deal is that lack of observability?
It's the thing that defines the amount of time it takes to bring your system up. And the bigger the system and the more complicated system, the more that matters. There's no really good way to take a deployed executing system and change it so that you can get feedback. If this was the system that's controlling your airplane, bringing down the controller of the airplane so I can instrument the system and figure out what's going wrong isn't very feasible. Lots of systems don't have the availability of the downtime that's required for intrusive debug methods. But that's kind of the only thing we have.
Once a problem is identified in terms of this signal didn't do what I expected because of this reason, fixes are very easy.
If during the verification of a complex design, there were a way to be able to simultaneously check everything or almost everything that was going on, that would be fantastic.
The ability to look at what's going on inside a chip as things are running in real time in the field is something that people have assumed to be impossible. It's so revolutionary that the world is built to not have it.
Observability in the field is going to be so big, and people say, well, why? What are you going to look at? It's like, I don't know. If I knew, it wouldn't be that big.
It would sure be great if you could look inside a running system and see whatever you wanted while the system was running in real time, even at 2 gigahertz, even 3,000 miles away. Well, we can do that. That's what the DesignInsight technology does. That's what we're bringing to market. I thought it was important also. That's why I built it. Being able to look inside a system, a running system, without disturbing it, to be able to see any signal at any time at full speed, even remotely. What are people going to do with that? Well, certainly when they see surprising behavior in the field, they'll be able to debug and to tune their systems. But I bet that our customers will do all kinds of interesting things with DesignInsight that we haven't dreamt of. This is going to revolutionize design. The way our customers are going to build better systems tomorrow than they build today is by being able to see inside the systems they currently have, to see which of the choices they've made worked out and which didn't, to see what kind of data their systems have encountered. What we're looking forward to seeing is just how innovative our customers are and what exciting things they do with this DesignInsight technology. This is the technology we've developed at Tabula. We call it DesignInsight, and we've just brought this to market.